Hello and welcome everybody to the Georgia Tech Graph Theory seminar. Our speaker today is Treglown from University of Birmingham, and he will tell us about embedding spanning structures into vertex-ordered graphs.
Thanks a lot. Thanks, Anton, for the invitation. It's always good to be in Atlanta, even if it is virtually. Today I'm going to be telling you about vertex-ordered graphs and embedding spanning structures into them. And this is joint work with József Balogh from the University of Illinois at Urbana-Champaign and Lina Li from Waterloo. So what's a vertex-ordered graph, firstly? So maybe you haven't seen that notion before. So it's a vertex-ordered graph is a simple graph, so just the usual kind of graph that we know and love, except for what we're doing here is we're giving some ordering to the vertices. Okay, so in this particular very simple example, we've got the vertices 1 up to 6. And the way we're looking at this is we're thinking that, say, the vertex 1 is less than all of the other vertices. It's smaller than all of the other vertices, so because it's given the smallest label, and so on. So 2 is the second smallest, and so on. Okay, so more generally or more precisely, a vertex-ordered graph, or just an ordered graph, so usually I'll just say it's an ordered graph, are graphs who have n vertices that are labeled 1 up to n. And again, the vertices inherit the ordering of the numbers. So 1 is the smallest vertex, 2 is the second smallest vertex, and so on. Okay, so that's an ordered graph. Now we have a notion of an ordered graph G containing another ordered graph H, and I've given you the formal definition here, but you don't have to read that, just look at this example. So here I've got a graph H, and I can't see it on my screen because the way my screen's set up, but I think it's labeled 1, 3, 4, 2. Hopefully that's correct from left to right. So that's the path of length 3 with the labels 1, 3, 4, 2. So if we look at G now, and we look at this red path of length 3, that's not a copy of H. Why is that? Well, it is a path of length 3, but if you try and map H onto the red vertices, you're mapping 1 to 1, which is good. But again, look at the pattern of H. We go from 1, 3, 4, 2. So we go from the smallest vertex to the second largest vertex to the largest vertex to the second smallest. Whereas this red path goes 1, 6, 5, 3. So we go from smallest vertex on the path to the largest vertex on the path to the second largest to the second smallest. So the pattern of how you go up and down, the relations do not match. On the other hand, if you look at the green path of length 3, that is a copy of H, because again the pattern is smallest vertex 1, second biggest number 4, biggest vertex 5, second smallest. So it's following that pattern there. So hopefully you get this idea that in the ordered setting, this is how we're embedding things. Okay, so so as I say here, and as you can see now, this is a very different problem. Embedding a graph in the ordered setting is very different to the unordered setting. So just because 2 ordered graphs have the same underlying simple graph, it doesn't mean that they're both contained in a particular ordered graph G. So one of them, H, might be in in G, and H prime may not be in G. Having said that, just a simple observation, there's only one ordered complete graph, KR, on our vertices. So however you label or order the vertices up to isomorphism, it's the same graph if you're looking at the complete graph. Okay, so that's just the sort of basic notion of vertex-ordered graph. Now, a lot of work has been done on Turán problems for ordered graphs. Okay, so in other words, how many edges do you need in an ordered graph to force a fixed H as a subgraph? Before I talk about that, I'll just give you a quick reminder about Turán problems for unordered graphs. So the Eddystone-Simonovitz theorem says if H is a fixed unordered graph, so it's just a simple graph, and if G is a sufficiently large n-vertex graph whose edge density is greater than 1 minus 1 over the chromatic number of H minus 1, then G must contain H. Okay. And here this condition is best possible. So if you look at the R-1 partite Turán graph, so R-1 classes, all possible edges between the classes equal size as possible, that doesn't contain any R-chromatic graph, and so that attains the bound in Eddystone-Simonovitz. Okay, so asymptotically, this is what this resolves the problem for unordered graphs, for simple graphs. So what about for ordered graphs? Well, Pach and Tardosh proved an ordered graph version of the Eddystone-Simonovitz theorem, and to state that, I need to introduce just another definition. So that is the notion of an interval coloring. So what's an interval coloring? So if you take an ordered graph H on n vertices, an interval coloring is a normal proper coloring of H. So the endpoint of every edge, the endpoints of every edge have different colors. It's a proper coloring, but moreover, each color class forms an interval in n. Okay, so you need that the color classes are intervals. Okay, so here's a very simple example of an ordered graph with just two edges. So this is a interval coloring using three colors, because the red class is an interval 1, 2, the blue class is trivially an interval, and 4, 5 induces an interval, and again it's a proper coloring. Okay, so that is an example of an interval coloring of using three colors, and actually it's easy to see that that has interval chromatic number exactly 3, that you can't use two colors in this case. Okay, now I can't, oh, I see now, I'm learning how to use Zoom. Okay, great. So one thing I've written down here is in general, even though say your underlying graph is bipartite, the ordered graph might actually have very large interval chromatic number. So this was a bipartite graph if you ignore the ordering, but it had interval chromatic number 3. And of course, you can see in general that you can have arbitrarily large interval chromatic number, even though say you're bipartite. Okay. So where does this interval chromatic number come up? Well, it comes up quite naturally in the analog of Eddystone-Simonovitz for ordered graphs. So Pach and Tardosh showed the following. So this statement's exactly the same as Eddystone-Simonovitz. We're just replacing graph with ordered graph and replacing the chromatic number with the interval chromatic number. Okay. So if G is an n-vertex ordered graph that has density greater than 1 minus 1 over the interval chromatic number of H minus 1, then G must contain H. Okay. And similarly to the Eddystone-Simonovitz theorem, this edge density condition here is asymptotically best possible. So here I've drawn the say R minus 1 partite Turán graph if H has interval chromatic number R. So I've got R minus 1 classes, all possible edges between the classes, and they're as equal as possible. But now, because we're an ordered graph, we have to give a labeling of the vertices. So here I'm labeling from left to right. So the leftmost vertex has label 1, the rightmost has label n. And again, simply this is the reason this doesn't contain a copy of H is that, well, if H has interval chromatic number R, this graph itself just has interval chromatic number R minus 1. So you can't place H into here, even though it only just fails to satisfy the Path-Tardosh condition. Okay, so that's nice. We've got an analog of Eddystone for ordered graphs. And okay, in general, this resolves the Turán problem for ordered graphs H, where the interval chromatic number is at least 3. So like in the unordered setting, the bipartite case is the interesting one. So in this case, the error term in the Path-Tardosh theorem dominates. So the question is, what is the truth in the interval chromatic 2 case? So there's a couple of surveys on that by Tardosh, but I'm not going to talk about that anymore. The reason I wanted to mention this is because I want you to sort of have this Path-Tardosh theorem in the back of your mind when we're looking at spanning structures later on. But before I change topic, before I talk about my main topic, I also wanted to say that as well as Turán problems for ordered graphs, there's also a lot of interest in Ramsey problems for ordered graphs. I just flashed some names at the bottom there. Okay, so this has kind of motivated us that we saw, okay, there's a lot of interest in ordered graph problems in general, but what hadn't been considered are spanning structures in ordered graphs. Okay, and they're very natural questions to consider, right? Because I mean, a whole host of results in graph theory concern embed your favorite spanning structure, give me a minimum degree condition, Dirac's theorem or something like that. The problem is, I think at first sight, maybe this doesn't seem as natural a question for the following, well, this is the following example that sort of makes you feel like that. So if we look for a Hamilton cycle in an ordered graph, well, we'd have to choose what specific type of Hamilton cycle. So let's say we're taking the Hamilton cycle, which is ordered cyclically, so from clockwise 1, 2, 3, 4, and so on up to n. Well, then, if you're trying to embed that in an ordered graph, there's only one way to place that in there. You're having to map 1 to 1, 2 to 2. So you have a Hamilton cycle if and only if you have the edges 1, 2, 2, 3, 3, 4, 4, 5, and so on. So unlike in the graph case where you've got many different possible edge sets that could support a Hamilton cycle, now you've only got one. So really what that makes you realize is, well, these kind of connected structures aren't good to look at in ordered graphs. What you want to do is look at disconnected structures, more precisely structures where you may be repeating many copies of a subgraph, a fixed subgraph, perhaps. So that's where perfect H-tilings come in. Okay, so what's a perfect H-tiling? So both in the ordered and unordered settings, an H-tiling in a graph is just a collection of vertex disjoint copies of H in G. Okay, so H-tiling is just vertex disjoint copies of H in G. And we say that a H-tiling is perfect if it covers all of the vertices of G. Okay, so a perfect H-tiling covers all the vertices of G. Right, so that's a natural generalization of a perfect matching, right? So if H is simply an edge, a perfect H-tiling is a perfect matching. But now we're allowing the tiles to be different at different H. Okay, so in this talk, I'm using the notation of perfect H-tiling, but sometimes I've used the notation of H factors, perfect H backings, perfect H matchings. It depends who my co-author is. So people have different tastes, what they call them. If you've seen any of these notation before, yeah, we're meaning the same thing. Okay, so we'll be looking anyway at perfect H-tilings. So let's just have our baby example again. So now I've got H being our path of length 2, and the pattern is smallest, largest, medium. So the green and red edges together give us a perfect H-tiling because they cover every single vertex, they're disjoint, and again, each of these paths follows the right pattern, smallest to the largest on the path to the middle value on the path. Okay, so that's an example of a perfect H-tiling. Are there any questions or anything at this stage from anyone? Okay, great. So again, before I delve into what we proved in the ordered setting, let me remind you what happens in the unordered setting, in the simple graph setting. So the seminal result in the area is the Heinel-Samrady theorem. And what this does is it characterizes the minimum degree that forces a perfect clique tiling in a graph. So if you've got an n vertex graph where R divides n, and your minimum degree is at least 1 minus 1 over R times by n, then you do have a perfect KR tiling, a tiling with cliques of size R. And again, crucially, this minimum degree condition is tight here. So even just putting a -1 in the minimum degree condition would make it false. And again, there's an easy example showing that. So now we've just taken the complete R-partite graph. So R classes and all possible edges between the different classes, no edges inside of them. But now, unlike Turan's theorem, what we're doing is we're taking the classes slightly different sizes. So all of the classes have size n over R, except for, say, the first two. So one of them has size n over R plus 1, one of them has size n over R minus 1. And in this way, you only just fail to satisfy the Heinel-Samrady theorem condition. So you just have minimum degree shy of that. But you don't have a perfect KR tiling. Why is that? Well, every copy of KR has one vertex in each class. So you can only ever cover equally amongst the classes. And because the classes have slightly different sizes, it means you can't cover every vertex. Okay, so that's the extreme example. I'd say it's what I'd call an example of a divisibility barrier, in a sense of it's a construction where maybe the parity of these classes has caused us some problem here. So have that in mind for the next couple of slides. Okay, so anyway, Heinel-Samrady gives you the threshold for a perfect KR tiling. The question now is, what about perfect H tilings in general? Well, Kuhn and Othus resolved this problem about a decade ago. And rather than state what they said precisely, let me try and give you some intuition here, what's going on. So they determine this minimum degree threshold for forcing a perfect H tiling for any fixed H. Now, for a large class of graphs H, the threshold is 1 minus 1 over the chromatic number of H times by n, maybe plus some constant term, but you can ignore that C term. So for many graphs H, it's this 1 minus 1 over the chromatic number times by n. Contrast that to the Edelstein-Simonovitz theorem, where it was 1 minus 1 over the chromatic number minus 1. Okay, and in this case, the type of constructions we get are what I'll call a divisibility barrier. So in the next slide, I'll show you an example of this, another example of this. But anyway, for many graphs H, you've got this sort of one type of behavior. Divisibility barriers are the extreme examples, and the minimum degree that forces a perfect H tiling is this barrier. But for the remaining H, the threshold is something else. It's actually a bit lower than what you get in this first case. And here we're replacing the chromatic number with something called the critical chromatic number of H. Don't worry what that is precisely. Kind of the definition of this critical chromatic number comes from the extremal examples. And these extremal examples are what we call space barriers. Okay, so all I want you to know from this slide is there's a dichotomy of behavior. There's, for some H, there's divisibility barriers that determine the threshold for having a perfect H tiling. For others, it's this space barrier. Okay, so let me give you some examples of what's going on here. So some examples of where divisibility barriers, so divisibility extremal examples, give the correct threshold. Well, we saw for cliques already, that was Heinel-Samrady theorem, told us that 1 minus 1 over the chromatic number of a clique times by n is the correct minimum degree threshold. Similarly, if you took sort of blown up copies of that, so your tile, your H is a KSSSS, again, you can easily see the same extremal example works. But you get other types of divisibility barrier as well. And maybe this example is more instructive for why we call it a divisibility barrier. So for any connected bipartite graph H, the extremal example is going to be a divisibility barrier, and that together with the Canother's theorem shows that minimum degree n/2 is the correct threshold for forcing a perfect H tiling in this case. So why is that? Well, let's just look at C4, but this example generalizes. So we're looking for a perfect C4 tiling. Well, let's just take two disjoint cliques, X and Y, where X and Y is equal as possible, but both of them have odd parity. Okay, so in this case, well, G has minimum degree about n/2, just shy of n/2, so just short of what's in the Canother's theorem. But it doesn't have a perfect C4 tiling, right? Because every C4 either lies entirely in X or entirely in Y, and so therefore you can only ever cover an even number of vertices in X and an even number of vertices in Y. So you've got some divisibility barrier here. The fact that X is odd size means you can't cover everything. Okay, so hopefully that's making some sense. Okay, so just some divisibility barrier preventing a perfect C4 tiling in this case. And then we also have the other case, right, where we're talking about space barriers, whatever they are. Okay, so there are examples of H where space barriers give you the correct threshold. Well, examples include you take what we had before, KSSSSS, but then just shrink one of the class sizes by 1. Now the threshold is different to the previous case. Also, if you take any odd cycle of length at least 5, you get something called a space barrier. So again, I'll just show you one example of this, and then you can sort of think how these examples generalize. So let's look at C5. So we're looking for a perfect C5 tiling. So the Canother's theorem tells us that if you've got minimum degree about 3n/5, then you have a perfect C5 tiling. And that's typed through the following example. So G has 3 classes A, B, and C, all possible edges between classes, but no edges inside of the classes. And now we've just changed the sizes of the classes. So in total, there's 5m vertices, but the smallest class A only has m-1 vertices. Okay, so this doesn't have a perfect C5 tiling, even though the minimum degree is just shy of the Canother's threshold. So why is that? Well, C5 is a 3-partite structure. So any copy of C5 must use at least one vertex from A, because G itself is 3-partite. So any copy of C5 uses one vertex at least from A. So therefore, in total, we can only find at most m-1 disjoint copies of C5. But we need m copies of C5 to perfectly tile G. So that's why we call it a space barrier, because that we run out of space. We need more space in A. Okay, it's not some divisibility barrier or something. It's just generally we just run out of space in G. Okay, so again, if you didn't understand all of that, just take with you the fact that in the unordered setting, there's 2 types of extremal construction: space and divisibility barriers. Okay, so what about the ordered setting now?
Can I ask a quick question?
Yes, sure.
So is this dichotomy between space barriers and divisibility barriers related with the question of whether or not there is a fractional H tiling?
Okay, so if there's a perfect fractional H tiling, that threshold, I believe, always occurs at the lowest threshold. So this threshold 1 minus 1 over the critical chromatic number of H. So this bottom threshold here is what gives you a fractional perfect H tiling. Now, using Samoredy's regularity lemma, you can transform that in a fractional perfect H tiling into a almost perfect H tiling, covering like 99% of the vertices. So that's why if you can avoid some sort of divisibility barriers, that's why the threshold can be made perfect at this bottom level. But if you've got some sort of annoying divisibility issues, then your almost perfect H tiling you can't modify into a perfect H tiling. So that's sometimes how you need this extra boost. So that's a good way of thinking of it. For almost tiling with copies of H, this critical chromatic number threshold is the right one. And then either you're done at this stage, or there's some annoying divisibility issues, which mean that you have to go a bit higher. Okay, yeah, nice. Okay, so that's the sort of dichotomy in the unordered setting. So what about the ordered setting? So what do József, Lina, and I do? So I grandly claim that we introduce a general framework for the perfect H-tile tiling problem. So what I'll tell you in about 10 minutes or so is that we modify the regularity method to be applicable to our order graph setting. So you'll see that there's some problems with using the regularity method, so Samoradi's regularity lemma in the ordered graph setting. So we sort of introduce a sort of way to think about things that avoids that. We also give some sort of absorbing argument, whatever that means. So what does that mean? It means if we've found 99% of the perfect H tiling, so we cover 99% of the vertices, we have some black box that covers the last remaining vertices. So I won't actually have chance, I don't think, to mention that too much. So, okay, so anyway, the idea is sort of our main contribution is this sort of general way of thinking about perfect H tilings. And then what we did is we apply this framework to the ordered setting, but for perfect H tilings, just for perfect H tilings with interval chromatic number 2. Okay, so that's kind of what we did. So in the next 10 minutes or so, I'll show you the sort of the intuition about the threshold, where the threshold lies for perfect H tilings of interval chromatic number 2. Then after that, I'll kind of give you some intuition about the methods we use. Okay, so let's now just fix our attention on perfect H tilings, where H is an ordered graph with vertex set 1 up to H, and you have interval chromatic number 2. Okay, so the first class of H we're interested in this case is when they have something called property A. So what's property A? Well, H has property A if it has no edges in the first half of its vertices or in its second half. Okay, so if you've got property A, there's no edges in the sort of vertices 1 up to H over 2 roughly, and nor are there in H over 2 up to H. So edges jump between these two classes. Okay, so if you have this property, sorry, if you don't have this property, then the minimum degree threshold for a perfect H tiling is determined by another type of space barrier construction. Okay. So again, let me give you an example, and hopefully you can sort of see how you might generalize this. So let's look at H now, which is a star with 4 leaves, and the root is labeled 1. Okay, so that's our sort of dummy or our baby case for H. So certainly this doesn't satisfy property A because you've got the edge 1, 2. So you really do have an edge in the first half. Okay, so it doesn't satisfy property A. So we showed in this case that minimum degree of about 4/5 forces a perfect H tiling. 4n over 5 in an n vertex graph forces a perfect H tiling. And that's best possible for the following graph G. So again, this black dot here, this black set B, means you've got all possible edges inside of this set of size 4n over 5. This smaller dot A has size n over 5 plus 1, and you have all edges between the classes A and B. Okay, so now what we have to do, because we're in the ordered graph setting, we're labeling the vertices, giving them an order. So again, we do it from left to right. So the leftmost vertex in A has label 1, the rightmost vertex in B has label n. Okay, and if you think about it, well, again, a perfect H tiling has n over 5 copies of H, but any vertex in A has to play the role of vertex 1 in H. Why is that? Well, it can't play the role of 2, 3, 4, or 5 because it would need a neighbor to the left of it. But it's an independent set A, so there's no neighbors. So again, every vertex in A can only play the role of vertex 1. And so in this case, we have too much space in A. We can only find copies of H that use, we need that every copy of H that use a vertex in A must use that vertex play the role of 1, but we've got too much space. We've got n over 5 plus 1 vertices that need to play the role of 1, but we only can use n over 5 of them. Okay, so hopefully that made some sense. That again, we sort of have, in this case, too much space. A is too big, or another way of thinking that is B is too small. Okay, so in general, if you're in this case when you don't satisfy property A, then the extreme example is going to be precisely this picture, but just with the ratios of A and B changed in order to get some contradiction like this. So, you know, if I had, say, on the left-hand side, 1 and 2, and then lots of edges, so we had 1, 2, and then 3, 4, 5 here on the right-hand side, then the ratio of this classes would change. 2 vertices on the left-hand side for every 3 vertex on the right-hand side. You can sort of play around with it and see how you generalize this in general. Okay, so that's one type of construction that comes up. Okay, so I've written now property A up again. So now what's property B? So property B says, however you have property B, H has property B, if however you partition the numbers 1 up to H into 2 intervals, then there's always going to be an edge going between the 2 intervals. Okay, so however you partition into 2 non-empty intervals, there's always an edge between these 2 intervals. Okay, so the previous slide dealt with H that didn't satisfy property A. So now let's look at H that satisfies property A and property B. Well, in this case, the minimum degree threshold is governed by the extreme example being a divisibility barrier. Okay, so more specifically, we show in this case, if you've got minimum degree n over 2 plus a bit, then you definitely have a perfect H tiling. And if you're below that, you may not contain a perfect H tiling through the following example. Okay, so again, I'll just focus on a specific H. So H here only has one edge. It has the edge 1, 5 and 3 other vertices. So it satisfies property A because it has no edges in the first half, no edges in the second half. And it satisfies property B because however you partition into intervals, you've always got that edge 1, 5 going across here. So this is really like a very sparse situation to be in this particular subcase. Okay, so our extreme example is a variant of our friend from the Canother's theorem. So we take, again, x and y being disjoint cliques of almost equal size. Now we take them to be not divisible by 5. Okay, and as always, because we're looking at an ordered graph, we have to give some ordering. So the vertices in x are all smaller than the vertices in y. Okay, so we're going from left to right again, 1 up to n, labeling the vertices. Okay, so what's the problem here? Well, why don't we have a perfect H tiling? Well, even though H is far from being a connected structure, it behaves a bit like a connected structure in the sense of every copy of H either lies entirely in X or entirely in Y, right? Because as soon as you embed the edge 1, 5, that has to lie either entirely in X or entirely in Y. Everything in between has to lie in the same class. Okay, so this is where the ordering really comes in now. So every copy of H either lies entirely in X or entirely in Y. And so then again, because these classes have some divisibility problem, they're not divisible by 5, we can't cover every single vertex in X and Y. Okay, so I think this example is instructive because it's showing, look, even really sparse graphs, you get these sort of divisibility problems coming in. Okay, so kind of those are sort of the two main constructions. And so far, what's occurring, right, is we're seeing divisibility barriers and we're seeing space barriers. So we're seeing things like what was happening in the Canofis theorem. But perhaps surprisingly, that's not the only thing that can happen. So other stuff goes on as well. Well, precisely one other type of thing goes on in the interchromatic 2 case. So again, H is an ordered graph with vertex set H and interchromatic number 2. So there are some types of H where the extreme barrier is neither space nor a divisibility barrier. It's what we call a local barrier, and you'll see exactly why we call it a local barrier in a second. So this graph H here is an example of a local barrier construction. So you can check it doesn't satisfy, it was not in any of the previous cases. So we showed in this, for these type of H, then again, minimum degree n over 2 in an n vertex graph, well, at least asymptotically, so being sufficiently above that forces a perfect H tiling. And again, n over 2 is best possible here. Why is that? Well, let's look at this graph G. G is the complete bipartite graph A and AB, but with an extra vertex added on. So A and B are independent sets, all possible edges between A and B. And then we've got an extra vertex on the right here. So again, we label from left to right. So the leftmost vertex in A is labeled 1. We keep on ascending. And then the very last vertex, this special vertex, is labeled N. And this guy sees everything in B, but nothing in A. Okay, everything in B, but nothing in A. So this structure has minimum degree about n over 2, but it doesn't have a perfect H tiling. Why is that? Well, precisely because it doesn't have a copy of H covering this last vertex, this vertex N. Okay, so why is that? Well, N is the largest vertex in your graph, so you have to embed the vertex 5 from H onto there. So you look and see, well, where would 2 go? Where would 2 be embedded? It would be embedded in B because that's where 5's neighbors are. But then there's no edge inside of B, so there's no vertex to play the role of 4. Okay, so if you're trying to find a copy of H, N plays the role of 5, but then you can't find the edge to 4 that you're looking for. Okay, so this is why we call it a local barrier, right? Because this local obstruction is stopping us from having a perfect H tiling. Okay, so I haven't stated to you the precise theorem because I don't want you to get bogged down with technicalities, but just in summary, we determine the minimum degree threshold for forcing a perfect H tiling for all ordered graphs H with interchromatic number 2, and 3 things can happen: a space barrier, a divisibility barrier, or a local barrier. Those are the extremal constructions. Okay. Again, just to emphasize, in general, these minimum degree thresholds can be wildly different to that of the underlying ordered graph. So just because the threshold for the underlying graph is whatever, the gap can be absolutely massive. Okay, cool. So that's sort of our results for interchromatic number 2. Now I want to tell you about the methodology. Okay, so I claim that we sort of do something novel when it comes to using Samoredi's regularity lemma. So to tell you about that, I first need to tell you what's the standard thing to do when you're using the regularity lemma. Okay, we'll come to that in a second. So before I tell you that, maybe I'll just give you the sort of baby case we're going to look at. So suppose we wish to find a perfect H tiling in the ordered graph G, where H is below. So it's just this bipartite structure. It's got interval chromatic number 2, and its underlying ordered graph is just K23. It's the complete graph, a bipartite graph with 2 vertices in one class, 3 in the other. Okay. Now we know from the Canother's theorem that the minimum degree threshold for forcing a perfect K23 tiling is about n over 2. Okay, so if you're above that, you have a perfect K23 tiling. Below that, you may not do. So firstly, how would we prove this, or how do Coulomb authors prove this threshold for perfect K23 tilings? Well, they apply Samarad's regularity lemma. So G is an n-vertex graph with minimum degree at least n over 2, so it's n over 2 plus a bit. They apply Samarad's regularity lemma to G. So what does that do? Well, what we do is, apart from some throwaway set V0, which is at the bottom there, which we're just going to throw away, we partition G's vertex set into equal size classes and a bounded number of these to boot. So these are a bounded number of classes. Now the edges between classes behave in a random-like way. So either a pair doesn't have any edges between them, or you have a random-like distribution of edges. So in these sort of hatched picture here, I'm just saying, oh, these edges are somehow distributed in a random-like way. We call these epsilon regular pairs. Okay, so again, applying the regularity lemma means that you've got a bounded number of classes that you've partitioned G into, where either there's no edges between different classes, or the edges are distributed in a random-like way. Okay. Now, the sort of standard thing to do in this case is apply the regularity lemma, and then notice that because we had large minimum degree, we had minimum degree above n over 2, somehow having minimum degree above n over 2 forces a perfect matching, which in turn forces a perfect matching-like structure in this Samaradi regularity partition. So in this case, we had 6 clusters, and because we had large minimum degree at the start, it must mean that we can pair off each cluster to obtain a perfect matching-like structure. So in other words, here's an epsilon regular pair, here's a random-like pair, here's another random-like pair, we've paired them all off. Okay, so of course, in general, you haven't got 6 classes, you've got a billion or something, but you can just, you pair each of them off, so you've got disjoint epsilon regular pairs. Okay, that's the really standard thing to do when using the regularity lemma. Then what you do is you zoom in. So you now zoom into an epsilon regular pair. So here's an epsilon regular pair I made earlier. You use the fact that the edges are distributed in a random-like way to conclude that actually it's got an almost perfect K23 tiling in here. So in your epsilon regular pair, the way you embed is you put 2 vertices, say on the left-hand side, 3 on the right-hand side, then embed another one, 3 on the left-hand side, 2 on the right, then flip again, then flip again, then flip again. So you get a very balanced tiling. And the point is, because the edges are distributed in a random-like way, you can actually find this almost perfect K23 tiling in this epsilon regular structure. Okay. Now, locally, that gives you an almost perfect K23 tiling. Globally, that gives you an almost K23 tiling because almost every cluster, sorry, all clusters are covered by this. And you've got some annoying V0 set, so you can never hope for getting a perfect K23 tiling. But this does 99% of the job. And then Kuhn-Authus or whatever, whoever goes along and just does the rest of the 1% using something, some extra step we're not going to talk about. But really, this is like the default thing to do when you're applying regularity lemmas, do something like this. Okay, so let's try and do that now in the ordered graph setting. So let's take an ordered graph G with minimum degree at least n over 2. Let's apply the regularity lemma. We can do that. We can just forget about the ordering of the vertices for now and just apply this. We can get these epsilon regular pairs and we can find this perfect matching structure. All of that just holds immediately. But then we get into problems, right? So now we're looking for a perfect H tiling where H is this guy here. So let's zoom in on one of these epsilon regular pairs. Well, suppose the left class, all of the vertices are smaller than all of the right class. That's completely possible. We could have just been, say, unlucky and had that all of the vertices on the left-hand side are smaller than all the vertices on the right. So, for example, they could be the numbers 1 up to n on the left and n plus 1 up to 2m on the right. Well, if that's what you're left with when applying the regularity lemma, you're in problems because every copy of H uses 2 vertices from the left class and 3 vertices from the right class. So you're not going to be able to cover in a balanced way. You're always going to be left with only covering at most 2/3 of the left class. Okay, so that does really seem like a big problem. And I really want to emphasize this property is kind of what hundreds of applications of the regularity lemma use. The fact that given any bipartite epsilon regular pair, you can embed any almost spanning bounded degree bipartite graph. That's a property for Hamilton cycles or whatever that you need to use. But in the order graph setting, you just can't do that. You'll always be in situations. There will always be situations where you can only use a certain proportion of the vertices from that class. Okay, so what do we do to get around that? Well, firstly, let's even take a step back and think, well, this was bound to happen, actually. Even if we hadn't thought about the regularity lemma, this was bound to happen. Because that argument I was telling you about was for minimum degree about n over 2, whereas actually we came up with some extreme example, some space barrier construction that had minimum degree 3n over 5 that didn't contain a perfect H tiling. So we always knew that something was going to go wrong here with regularity lemma because we just had some extreme examples. Now, this is indeed our extreme example. So minimum degree 3n over 5 plus a bit does indeed ensure a perfect H tiling in this specific type of H. So why is that? So what do we do? So kind of, if we're sort of going to day one, how do we try and approach this? So roughly speaking, what we did is the following. We said, well, at minimum degree 3n over 5, what structures can we get in the graph? And let's not even care about their orientations, just what structures can we get? So we're looking for a perfect H tiling, but actually at minimum degree 3/5, that's kind of a natural threshold for another type of graph. And at first sight, it just looks like I've just got rid of the ordering of the vertices of H to create H prime and added a couple of edges. But in some sense, H prime is a very natural, if you think about it or haven't experienced in this, it's a very natural one to consider because it's a complete 3-partite graph. So it's a complete 3-partite graph, and somehow having a 3-partite graph when I'm trying to embed a bipartite thing gives you some room to maneuver. Okay, so our first thing was, okay, we can guarantee a perfect H prime tiling just using Knorth's theorem. So maybe we can get lucky and say, well, a perfect H prime tiling, if you label cunningly, or if you're always lucky, you can get a perfect H tiling from that. But of course you can't, right? Because you can just easily label H prime in such a way that it doesn't have a copy of H. So, in H, you've got the edge 1, 3, but in H prime, you don't have the edge 1, 3. So it's no good just sort of just taking your favorite H prime and hoping, luckily, that the numbers work out and H actually lies in H prime. So kind of what we do is so roughly what we do is the following. So we sort of apply the regularity lemma and sort of find blown up versions of H prime in the graph. So again, maybe it's like instead of H prime, we've got epsilon regular pairs replacing the edges here. And what we can show is that actually, if you choose the sort of right blow up version, then you can show that however H prime is labeled, you have an almost perfect H tiling, no matter how you've ordered the vertices. Okay, so then that allows us to get us an almost perfect H tiling. So we kind of tile using the regularity lemma some intermediate graph that has this nice flexible way of however you order the vertices, you can still get an almost perfect H tiling. Okay, so that's the general sort of setup for a general H, so the general framework we introduce, we have this sort of intermediate step of finding these dense graph H prime that are flexible in the sense of regardless of how the vertices are ordered in H prime, each of them can find an almost perfect H tiling, and then piece them together, you get an almost perfect H tiling of the original ordered graph. But there is a balancing act here, which makes it, I guess, this is the thing that makes it challenging, right? What you need to do is find these structures, these intermediate structures that are not too dense, because you need them to be sparse enough so they exist in your graph, but dense enough to have this property that however you order the vertices, you're still fine. Okay, so there is some balancing act here, which I'm not going to go into. And then I guess there's the final thing to say is, well, we use the absorbing method to cover the last remaining vertices in G. So we basically have a black box that says no matter what a H is, if you've covered 99% of the vertices, we've got some argument that says you can just cover the last 1% as well, but I don't have time to talk about that. Okay, so just to finish off then, so that was the sort of general framework within the methodology. So just some open questions now. Well, hopefully you can see there's lots of different, basically tons of open problems, right? Because no one else has looked at spanning structures in ordered graphs before. Now, okay, some structures aren't natural in as spanning structures in the ordered setting, but there's lots of ones that are. For example, just to pluck one off from thin air, what's the minimum degree in an ordered graph that forces you to contain a collection of a bounded number, say 2 cycles that cover 2 ordered cycles that cover every vertex? So maybe you don't cover with a Hamilton cycle, but maybe you cover with 2 ordered cycles. Okay, so you can still ask natural spanning questions for ordered graphs, but you can also ask questions that aren't about spanning structures. So here's an example. What's the minimum degree threshold for forcing an H tiling covering a given fraction of the vertices of an ordered graph? So maybe you want a H tiling covering a 50th or 99% of G, or your favorite fraction. What minimum degree forces that? So that's been known for 20 years by Konosh's theorem for unordered graph, the simple graphs. What about the ordered graph setting? You can look at these other questions, but in the setting of edge-ordered graphs rather than vertex-ordered graphs. So Turán and Ramsey problems have been looked at in terms of edge-ordered graphs. So you can ask the same kind of questions, but for spanning and linear size structures in edge-ordered graphs. And you can look for other structures as well, linear size copies of them. So maybe you want a tree covering a specific tree covering 50% of your vertices in your ordered graph. So yeah, basically there's tons of open questions, but that's where I'd like to finish.
Thank you very much, Andrew. Let us all thank the speaker. Are there any questions?
Can I otherwise just ask, sorry that I missed the beginning of the talk, but so what about this ordered concept in the concept of random structures? What is known, or has this been looked at?
So you mean you take a like GMP and then an ordered version of GMP or something?
Yeah, so like something like that. Like maybe the question is like, how do you define the order, or there it doesn't matter because by symmetry.
I mean, essentially, nothing is known about this in the literature, and I've never thought about it. So I guess it probably won't make any difference most of the time. I guess the only time, so I guess in this, the reason why it made why things are kind of different here is because for the problem we're looking at, the thresholds somehow depend on the chromatic number. So if you've got a problem maybe where the chromatic number of the structure you're looking at is sort of a parameter governing it, I can imagine a situation there when it might be interesting the problem might be interested in ordered graphs.
Uh-huh.
But yeah, I don't know if I mean it's 10 o'clock here, so I'm not entirely with it. But I don't think off the top of my head. Certainly, some problems won't be interesting in for random structures. But I can imagine a situation where there would be, and as I said, in my situation here, this is the issue is that it's because it's somehow the chromatic numbers is governing the thresholds. That's where maybe it becomes interesting.
So you mean that maybe if one finds an example where you start off the graph with you have some information about the chromatic number, and then once you start taking some kind of going to some subgraph or something, when the chromatic number changes in some complicated way, those are the setups where this. I
mean, I'm not saying that's the only setup. I'm saying this is kind of what happened here. But
I see.
Yeah, I don't know. I don't know. I haven't given any thought essentially for random structures. But yeah, that's a natural thing to ask. Thanks, Lutz.
Any other questions?
I have a question. Hi, Andrew. So you can also view the high-symmetry theorem as if you look at the complement of the graph as an equipartite coloring theorem. Does something like this holds here as well?
Good question. So I haven't thought about that before. So I guess what we're saying here is, so again, what Richard's saying is that the complement of the high-symmetry theorem says if you've got a bounded maximum degree, then you have an equitable coloring, say using our colors where every class has equal size. So I guess you do get, the problem is for complete graphs, what I was kind of indicating at the start, for complete graphs, the problem is solved already by high-symmetry theorem in the ordered graph setting. So I guess what you say in this setting, sort of the analog of high-symmetry theorem for ordered graphs, is saying something about equitable interval chromatic interval colorings, equitable interval colorings. So that analog will hold, but that's just immediate from high-symmetry. So kind of the interesting cases for ordered graphs, perfect tilings for ordered graphs, are when you haven't got a complete graph. The tile isn't a complete graph. Am I making some sense here?
Yeah, thank you.
Yeah.
And another question, can you recover the usual results from this? Like, is there some way to encode, let's say, Kuhn-Oster theorem by choosing the right labeling?
I haven't thought about that. So for Turán problem, the way that it's set up, or Pachtardos set it up, does imply the Erdős-Stone-Simonovitz theorem, because they take classes of, they talk about families. You want to find, instead of a copy of H, you look for a family of ordered graphs, say, and in that sense you can recover the original Erdős-Stone-Simonovitz theorem, because you just take all ordered versions of your underlying graph as your family. But I haven't thought about it. I suspect not is the answer, or I suspect maybe you can get something like the almost tiling threshold result. But as I was sort of indicating, like almost tiling is kind of a natural threshold, and then you get some extra problems with some divisibility barriers or local barriers. And I think that's the thing that makes this problem, I guess, rather different to the Kuhn-Oster theorem.
Thanks. And is this local barrier, is it basically saying that every vertex has to lie on a copy of what you're looking for, or is it something more?
Yeah, so the local barrier is that this was an example where a vertex didn't lie in a single copy of H. So in general, you're going to get these local barriers where you've got, say, some vertex, and it's the cases where it's the extreme vertex in H, the smallest or the biggest, and say it's the biggest, and it's got some neighbor, which in turn has a neighbor going after it. So it's sort of this kind of structure. So when you get these kind of things, you can always get the divisibility, so the space of the local conditions. It's just that for other cases, that's not the dominant one. These local and divisibility barriers, at least in the interval 2 chromatic case come about when when half is the correct threshold, n over 2 is the correct threshold. So, I mean, you can, for any graph H, you can come up with these local divisibility and space barrier constructions. It's about which one is the dominant one, I guess, in each case. But yeah, these local issues come about with this kind of structure in your graph. Okay.
I also have a quick question. I guess related to what Richard was asking earlier. Say I have a graph H that is unordered, and I want to find the tiling of an ordered graph with the condition that I want all of the copies of H to be ordered the same, but I don't care what the ordering is. Is this a meaningful sort of question to ask? I guess it's another way to ask this is like, if I have an H, what is the worst order or the best ordering for it?
Yeah. So are you saying that all the tiles have to be exactly the same?
Yeah.
Okay. So I think then it's just a case of you just do the problem for each one, and okay, you work out which it is. I mean, in general, the worst case isn't going to be that interesting, in the sense of, as soon as you have, if you think about it, as soon as you have the edge 1, 2, as soon as the edge, the smallest and the second smallest vertex are adjacent in your graph H, then actually you need minimum degree 1 minus 1 over r times by n, where r is the number of vertices in H. So actually, kind of, you get to really the worst case. Like I guess what I'm saying is that ordered graphs H, which have the edge 1, 2, behave like a complete graph. So that's a nice exercise or thing to think about, that any H with the edge 1, 2 behaves like a complete graph in terms of these extreme examples. So in that sense, the worst case is not interesting, because it's actually quite easy to solve. The best case, I guess, I don't know what the best case off the top of my head is for everything. I guess, though, a sort of related nice question is the question you weren't asking about. If you're basically allowing, maybe you're allowing a case where 99% of the copies of H have to be a certain type of ordering, but you're allowed some extra stuff. You're some extra copies of H which can be ordered slightly differently. So I imagine in that case that would always be like a lower threshold, like a space threshold, because kind of if you choose the nice last 1%, maybe you can always avoid these divisibility and local barriers. So maybe the answer to your question is that actually space barrier should always be like the best case, but I can't think off the top of my head if that's definitely true or not. But probably these space barriers are always the worst. Those are the best.
I see. Okay. Thank you. Are there any more questions?
Yeah, maybe. So, do you see a chance to prove these things in an abstract way, basically showing what you just said, that the space barrier is always the best, without knowing it? Or do you think, or do you have a conjecture of what should it be, and one should rather go for that?
I don't know really what to say about that. So do you mean just in general, or for the ordered setting?
Yeah, so is there any chance to prove a theorem that says something like, if you are able to break this space barrier and the divisibility barrier or the local barrier, if you kind of magically over all of those, then you get it, but without knowing what those are exactly?
Yeah, so I don't know about a really meta big general theorem. I haven't thought about that. I mean, you've seen stuff I've done, Richard, right, with like this complexity side of things, where we do say like, oh, if you're
that's what I'm thinking of.
Yeah, so there are things that basically say, there are results that basically say if you don't have a divisibility barrier, then you can find your perfect H tiling as long as you're above the space barrier threshold. So certainly there are results like that. I haven't thought, but I've only thought about that in the unordered setting. I haven't thought about how do you generalize that. And so I haven't thought if these local barriers cause any issues. I suspect actually, my feeling is probably you can prove some result like that for ordered graphs. So I assume that something like that is true, but I don't know how abstract you want to go in your statement, Richard. So I can only probably say just for ordered graphs or something, probably something that should hold. But I haven't given it loads of thought. Okay.
All right, any more questions? If there aren't any more questions, then let us thank Andrew again.
Thank you, Andrew. Nice
Thank you.
talk.
Thanks, Lina.
And our speaker next week will be Chonghong Liu from Texas A&M.